I want to thank the Simon's collaboration and want to thank everybody in the collaboration for a very helpful dialogue over the years. I really learned a great deal. So I actually went back to look at some of the talks I gave over the years. At the beginning, we were doing fractons with a lot of people in the audience. And then at one point, the fracton project led to this idea of sequential circuit with David and the mic, which actually turned out to be a stepping stone for me to jump into something slightly different. So we got from this idea of sequential circuit to defects, and this is with Nat, and a lot of inspiring discussions with Xiaogang, especially with Natty and Shuheng, that led me to think more about defects and back to topological phases and transitions, not so much about fracton anymore. And then with Wenjie, we did more about defects in 3 plus 1D and then 2 plus 1D. And then about the connection between sequential circuit and generalized symmetry. And this was last year where I just put out some even more crazy talks. And this year, this project was originally a rather standalone project where we were thinking about SPT transitions and somehow on Klein bottle. So we were almost finishing the draft and ready to put it out, thinking that, oh, it's a simple story. And then Vibhu, my student somewhere, asked a very important question that led to this whole second part about emergent symmetry that I mostly want to talk about today. So I think this realization about what it means, for me at least, means to have emergent symmetry and its potential implications is what I want to talk about, and hopefully this will lead to much future work. Okay, so this is definitely not done. We're just getting started. I think some idea about how to think about symmetries and what they mean about for phases and phase transitions. Okay. Yeah, so this work is done with Vibhu and Bowen, who are very happy that both are here. So yeah, if there are questions that I cannot address, please find them. Okay, let me get started. Yeah, so I'll start with some simple examples of SPT that I'm sure a lot of people are familiar with. So this is 1 plus 1D SPT with Z2 cross Z2 symmetry. So it's you can think of a Haldane phase or any other ways of realization. And one very prominent property that allows us to detect this SPT order is by putting the system on the ring, so we don't open a boundary or anything, so just a closed ring. And what we can do is to put a pi flux of the first Z2, and then famously, the state on the ring, the ground state, will carry a charge of the second Z2. So it's associated with the projective representation and all that, but we can just do it on the ring with a flux and charge. Okay, and the story can be very easily generalized to 2 plus 1D, except that we need yet another Z2. When we put this SPT on the 2D torus, what we can do is to put the pi flux of the first Z2 through one of the circle, and put the pi flux of the second Z2 through the other circle, and then the ground state has a Z2 charge of the third Z2. So you see why we need more and more Z2 components in the symmetry to see something like this. Okay, so this is all well understood. And then the question we were wondering about is, how can we do this for the single Z2 SPT? This is my favorite SPT. And the question is, can we do something by flux and charge and just detect it that way without looking at boundary or anything? Okay, so it's not obvious because there's only one Z2, so you can insert some Z2 flux. It doesn't immediately give you a Z2 charge. But what we realize is that actually, if we don't restrict ourselves to torus, if we put it on the Klein bottle, then problem solved. So you put the SPT on a Klein bottle, So no boundary, still closed surface. And then put a pi flux of the Z2 through this orientation reversing direction, so in that particular direction. And then what happens is that the whole ground state will carry a Z2 charge. Okay, so it may not immediately be obvious, but let me try to argue why that's the case, why people are laughing. Okay, let me try to argue why this is the case. Okay. So we go back to Levengood, where it was known that the SPT, if we couple to the Z2 gauge field, if we gauge it, it becomes this famous topological order of double semyon, where the Z2 flux is a semyonic semyonic degrees of freedom. So that's why it's a non-trivial SPT order. And then this operation of inserting a pi flux, if we think about it in this gauge theory picture, what happens is that we create a pair of semyon, these two pi flux, and then we drag them all around through this cycle, and then annihilate them, just put them back together, annihilate them. But if we do this on this particular cycle on Klein bottle, you'd see that the one of the semyon going around the cycle and it goes to the other side of the surface. They don't go back together, right? So one is on top, the other is at the bottom. And what happens is that the semyon becomes the other semyon, the other anti-semyon. Sometimes we call it very confusingly the anti-semyon. And then if we fuse them, it actually fuses back to the Z2 charge. So that's just a property of this double semyon gauge theory. So if we then come back to the on-gauge picture, that means if we literally drag a Z2 defect line along this cycle, the ground state will carry a Z2 charge. Yes? Can I imagine this is like effectively inserting like a time reversal? I would want to interpret it as a spatial reflection flux. A time reversal is a little tricky, but yeah, I'll talk more about reflection symmetry. Yeah. Okay. All right, great. Okay, so then we can say more maybe about the transition. So this is very much following ideas in this paper by Rubin and all, where so they give examples about transition, like in 1+1D with Z2 cross Z2 SPTs and 2+1D with Z2 cross Z2 cross Z2 SPTs. But very similar idea that inserting flux gives you some charge difference on the two sides of the transition. Then at the transition, you might expect to see some degeneracy. Of course, it actually has not much to do with the nature of the transition. It can be first order, second order. It can even be an intermediate phase. But because of this, as long as they meet somewhere in the middle, this will be true, that there will be a degeneracy between charged and not charged ground state if we put the whole system on a Klein bottle and insert a pi flux in the right direction. Okay. Yeah. So this has nothing to do with the nature of the transition. It's just saying that anywhere in the middle, there will be such a degeneracy. Okay, so we did some more concrete work to show that this has to be the case. So we used this very concrete lattice model called pivot Hamiltonian by Nat and others, where you can tune between a trivial symmetric phase. So this is a trivial symmetric phase, and then the SPT phase, and then tune some parameter to go in between. I better use this thing. Okay, and this whole model has a Z2 symmetry, so you can have a whole phase diagram between trivial symmetric phase and non-trivial SPT phase and some ferromagnetic phase. Okay. Right. Then we start from let's say the SPT phase side, just the exactly solvable Hamiltonian, and put it on torus, put it on Klein bottle, and then insert a defect line in the correct direction. And then we can check for the ground state. And on one side, the ground state is not charged. On the other side, the ground state is charged. So this is a nice calculation done by Vibu. And then we can look at some transition point. And the only feature I want to draw your attention to is that there's degeneracy when we put the whole thing on a Klein bottle and insert the flux, then we see this degeneracy between charged and not charged states. In all the other cases, there's no degeneracy. So this is just some support of what I'm trying to claim. Okay, is there any question about this part? That's basically the story of this work. Yes?
With the final J term on or
not? Right, sorry. You're asking for this plot. I think this plot is at this multi-critical point. What? Why is it jumping like that? Sorry. I think this plot is at the multi-critical point, but as I said, this doesn't really matter. That the degeneracy will be there as long as we're along this line, this alpha equal to 0.5 line. So it's even there in the ferromagnetic phase. It's basically an anomaly between this, what people call SPT entangular symmetry and the Z2 symmetry. It doesn't affect that. It's a symmetry anomaly thing. The anti-commute, basically. Yes? Great question. Okay. Now I can move on to the next slide. That's exactly what I want to talk about. Okay. So like I said, we were happy with this work. We were like, okay, we did the numerics and we can publish it. And then Vibhu asked a very important question, like also asked by Natty and Drew, that if we think about what's the difference between torus and Klein bottle, the difference is that we can imagine that the Klein bottle can be obtained from the torus by inserting a so-called reflection defect. So you start from the torus where you identify a pair of boundaries, and you reflect one of the boundaries without reflecting the other, and then connect things back together, you get the Klein bottle. Right? So Klein bottle is kind of like starting from torus and inserting a reflection defect. And then the question is, why reflection symmetry is playing a role here? We talk about this SPT forever. We always say it's a Z2 SPT, right? Nobody said it's a Z2 plus reflection SPT. So what exact role does reflection symmetry play in the story? Right. So one thing we know for sure is that this reflection symmetry is not needed to protect the SPT order. We know that it's fully protected by Z2. That's no question. Okay? But it can be there at particular point in the phase diagram, like the pivot Hamiltonian we were looking at is explicitly reflection symmetric, right? It's a very nice form, so explicitly reflection symmetric. And then what I will try to claim is that we should think of it as an emergent symmetry for the phase, even though usually we talk about the phase as in terms of Z2 symmetry, but this reflection symmetry somehow emerges. Okay, let me try to argue for that. That's a main part of my talk. Okay, right. So let's come back and look at this Hamiltonian. So this is just the SPT point. It's exactly solvable SPT point. No ambiguity about this ground state or anything. So the Hamiltonian is like there's a single x in the middle, and then control Z, control Z, control Z on all the edges. So 6 control Z on all the edges to just add some phase factor with this x. Okay? And then the nice thing is that, of course, all the terms commute, and this is exactly solvable. And you can check that the Z2 symmetry is this nice Ising-like Z2 symmetry where you just flip the spins. So with this Z2 symmetry, there's a whole phase surrounding this point. That gives you the SPT order. Okay. And then, of course, we can just take the lattice and do a reflection symmetry. And this point, this particular Hamiltonian is also reflection symmetric, right? Because it looks so nice. So you literally move the atoms around, and the term remains invariant. Okay. But of course, because we know the phase is only needs to be protected by Z2 symmetry, So we could potentially add Z2 symmetric, but not reflection symmetric terms. Okay. So you can explicitly add terms that break reflection symmetry, and that'll be fine, because as long as the term is not too big, we know that as long as Z2 symmetry is protected, the system will be gapped. It remains in the same phase. Nothing dramatic happens, although this reflection symmetry is explicitly broken. Okay. But what I want to claim is that reflection symmetry actually reemerges as long as you're in the same phase. So how do I see that the reemergence of the symmetry? I'll go back to Hastings and Wen, using this idea of so-called quasi-adiabatic evolution, that as long as you stay in a gap phase where the Hamiltonian don't close gap, then the ground state will be connected through a so-called quasi-adiabatic continuation. I don't want to write down the formula for that evolution because it looks horrific, but I just want to say that you can think of it as a finite time evolution with local Hamiltonian terms, but those local Hamiltonian terms have tails. That's why it looks horrific. But it's exponentially decaying tails, so for all purpose, it's roughly, I'll just interpret it as local Hamiltonians. And then what happens is that under this evolution, the ground state maps to the ground state, and then we can use the same evolution to conjugate whatever reflection symmetry we started with to get the new reflection symmetry for the ending ground state. Okay. And then, of course, if originally we had a ground state that's invariant under the original reflection, we had a new ground state that's invariant under the new reflection. So that would be our emergent reflection symmetry. Usually we don't like this kind of operator to be the symmetry because it will look very ugly. It's generically non-on-site, meaning that you don't just take one atom to the other. You follow this movement of atom with some finite time evolution generated by local Hamiltonian terms with tails. So it's very ugly. It's not on-site, it has tails, and it works only on the ground state. It's guaranteed to work only on the ground state. But if we only care about the low energy physics, here is gap phase, so we'll only care about the ground state, then we will say that the reflection symmetry reemerges. Okay. So let me just compare these two, compare the Z2 symmetry with the reflection symmetry. Yeah, maybe I can address the question, but yeah, go ahead. Right. The mic.
The most fancy version of emergence means in the microscopic level you don't have the symmetry, but after you zoom out you find this thing emerges. And I think you almost achieve that. But there seems to be one thing you rely on the lattice level, right? So it's like one of the realization actually does have the reflection symmetry. So that's something you actually borrow from the microscopic detail.
Oh, you mean that there are specific points in the phase diagram where this symmetry looks nice?
Right.
Yeah, while in some, let's say, CFT, it might be that you don't really have a realization where it looks exact. Yeah, so yeah, for gap phases, I don't know, maybe you can always find one point. I don't know. I'm not...
Right, so I guess one question is whether you can do really without assuming anything on microscopic length scale.
Yeah, that's, you're getting, again, ahead of me, yes. That will be the way I'll try to define emergent symmetry more carefully. So this is just an example illustrating how it can come from in this model.
Great, thank you.
Yeah, sure.
Symmetry from the other crystalline symmetry, like lattice translation?
Or any symmetry.
Or any symmetry,
Any symmetry, any internal symmetry, lattice symmetry, like you said, I can always do quasi-adiabatic continuation. So again, that will be done in like 2 slides from here. So it seems to be like I'm saying that anything can emerge. And that's, I think, the corresponding statement for you may be that any defect in gap phases are topological defect. I'm not sure.
But is there anything special about the reflection
there
in your
will be
model?
something special
Okay.
about reflection symmetry because we see that it induces some non-trivial response. Right? We put it on Klein bottle, it induces some non-trivial response. And we will have a way, that will be our way to define what is the non-trivialness about the emergence of the reflection symmetry.
Your underlying lattice model does not have reflection symmetry.
At one point it did.
Earlier it did, but at this stage it's not there.
Right.
So how can you put such a system on a Klein bottle?
And it should still be doable. The Hamiltonian terms might not look exactly the same everywhere, but you still have a way to close the boundary.
But that you could do with any transformation which has nothing to do with symmetries.
Yeah, that's something I want to claim about emergent symmetry. These are all great questions, and hopefully maybe 10 slides from now, I'll be able to address them. Yeah, thank you. Thank you. You guys are all asking the key questions. Okay. Yes?
This is the reflection flux and the Z2 flux.
Yeah, they're both there.
They both are, and they're in 2 different cycles. I can't quite picture it.
I need to think about it.
Okay.
Probably, yeah, perpendicular, yeah.
Did you want the reflection vertically in the picture she was drawing in the the other way?
Okay.
Yeah, exactly, yes. Yes, thank you. Otherwise, they won't know each other right there. Kind of. Oops, sorry. Okay, so let me, I can see that people cannot wait, but let me just pause a little bit and talk about this terminology of what we call emergent symmetry versus defining symmetry, or maybe people call it differently, but in this paper we call it defining symmetry versus emergent symmetry, where the Z2 symmetry is what we consider as the defining symmetry, where it's necessary to protect the order. If it's not there, then we don't even have an SPT order anymore. But the reflection symmetry is not needed to protect the gap phase. Right? It can be there, it cannot be. It does not have to be there. So the Z2 symmetry needs to be exactly preserved at the lattice level, while the reflection symmetry does not. But as I try to claim, that it always emerges at low energy as long as we're in the same gap phase. But then the common feature of these two is that inserting defects of them can induce non-trivial response at low energy. Okay, so that will be our key of talking about what kind of symmetry is interesting. That the kind of symmetry whose defects can induce non-trivial response is the kind of symmetry that's an interesting symmetry. Yes. So. I think the continued, the emergent.
Very fancy Klein bottle.
No, Klein bottle is the same Klein bottle. It's the
But doesn't it
the
do like
unitary
ordinary
part.
reflection? It does like an ordinary reflection with some very complicated unitary too.
It's the ordinary Klein bottle, but with the terms that's a little ugly. The Hamiltonian terms. Yeah, it's the same Klein bottle.
I have a follow-up question about that. So, kind of dressed unitary, right? It preserves the ground state, but it doesn't preserve the Hamiltonian.
It doesn't preserve the Hamiltonian.
But then how can you?
So it's emergent only at low energy.
But then to put.
So the Hamiltonian, no, I'm just saying that the ground state is still gapped. That's all I care. The excited state, I don't know, maybe. Yeah. Oh, yeah. Well, if you literally conjugate the terms, the Hamiltonian will be very ugly. So what we could do. Yeah, we'll have the same ground state. That's all I care. I don't care the Hamiltonian. Maybe the excited states are different. I will have a new Hamiltonian which have the new ground state as the ground state. Right.
There's no Hamiltonian because as you cross from point to point,
Yeah.
you cross this reflection defect. You have to apply this transformation, but that's not a symmetry of the problem.
Yeah,
I believe this
I
is the
see your
same
point,
question
yes.
the same question that, yeah.
Yeah, I totally see your point that if you directly try to do this to the Hamiltonian, it's not obvious that it can be done because the Hamiltonian doesn't have the reflection symmetry anymore. So all I'm trying to claim here is that there is still a gap Hamiltonian that will have the ground state. I don't have a slide showing that. I'm pretty sure it should work. Let me maybe try to address that later after the talk. Yeah, thank you. Yes.
So you can choose a different parent Hamiltonian for that ground state, which is just a conjugated original Hamiltonian.
Yeah.
And then that Hamiltonian, you can insert this like.
Yeah. And along the defect line, it might even look different from the bulk. But yeah, I'm okay with different Hamiltonians. I'm going to try to, okay. I'll need to do more work to show you that this should work, but maybe it will become slightly better once I connect this to higher form symmetry, which people I think are more comfortable being emergent. And maybe I can address the question there. Okay. Yes. Oh.
Then it's still perfectly a Levengood state from the Z2 point of view, if I don't consider the reflection symmetry.
Okay.
But if I turn it on Klein bottle, I insert this reflection flux and this Z2 flux, I think it would also contribute an additional charge.
But you have an additional, let's say, SPT protected by both the reflection and the Z2, right? That's what you stack on in the first step.
Since that it's still in the Levengood universality class, and that charge could be changed just by stacking something like not a Z2 SPT.
Yeah, I'm saying that this reflection symmetry doesn't have to be preserved.
So it's already a bit. So in the third bullet point, how does it depend on the fact that it's a Z2 symmetry SPT, or if I change it to other group?
At this point?
Yes. How does it depend on?
Oh, the emergent symmetry will depend on which phase you're in.
I mean, this reflection symmetry always emerge.
Right. So I need to talk about what is non-trivial versus trivial emergent symmetry. If you're in a trivial Z2 SPT, you can also say, oh, I have emergent reflection, but that reflection will be kind of boring because you put it on Klein bottle, you don't see anything. Yeah, I need to define what is trivial versus non-trivial emergent symmetry in a few slides. Okay.
Maybe we should let you continue.
Thank you. Right, okay, so at this point, I will try to take the analogy to higher form symmetry, which people are more comfortable being emergent. And we'll maybe address the question of how the Hamiltonian maps. Okay, but this is, let's say, the toric code, where it's a two-dimensional lattice model, where we have the plaquette term and the vertex term, and this is an exactly solvable point, so very nice. On the lattice level, this particular Hamiltonian involving only these two terms have the special property that it has an explicit one-form symmetry on the lattice level, right? So you can take all these so-called vertex terms and then and including the non-trivial one, going along non-trivial cycles, and say, okay, they form the so-called one-form symmetry. Okay, and we can explicitly preserve that symmetry, but all we know about toric code is that you don't have to. If you're away from this exactly solvable point, the way we can think of this one-form symmetry is that this is basically the loop operator of one kind of enyon, one kind of boson, and that exists in the whole topological phase. So this is a phase diagram, famous phase diagram of toric code with magnetic field in the x direction and z direction, and there's a whole topological phase here, even though the one-form symmetry is explicitly preserved only along one of the lines. Okay, and when you get off the line, this particular symmetry is explicitly broken, but we don't care. We always say that this one-form symmetry reemerges, and we can insert defects of them. The defects will be the enyons of the model, right? And right, so in this sense, this one-form symmetry in the toric code is also an emergent symmetry. Well, this is, of course, better accepted than reflection symmetry being emergent in the SPT model, I guess. Okay, so right, so now the question, I'm finally addressing this question, which has been asked many times. How do we identify emergent symmetries? Right? Given a gap phase, which one do we call gap emergent symmetry? And what are the non-trivial ones? So far, what we have been doing is to start from a nice-looking Hamiltonian, start from a particularly nice-looking point in the phase diagram, and just by looking at it, observe any accidental symmetry it has. Right? It could be reflection, it could be anything. And then use quasi-adiabatic continuation to say, okay, it extends to the whole phase. Okay, so that's like almost a too simple-minded argument, which would work for everything, right? For any symmetry that you want to talk about. So it seems like there can be a lot of emergent symmetries. So you can find toric code on square lattice, triangular lattice, whatever lattice. Then you can have a ton of emergent symmetries. But then, for example, this particular pivot Hamiltonian for the SPT order, there's translation symmetry, there's reflection, rotation, global Z2, and indeed each Hamiltonian term is preserved because it's a commuting projector Hamiltonian. So do we call that also an emergent symmetry? We can, but not all of them will be interesting. Not all of them will give you non-trivial response at low energy. Okay. So the thing is that if we just do this, there will be too many emergent symmetries, but only very few ones are interesting. And the ones that are interesting are the ones whose defect induce non-trivial response at low energy, and we need to say which ones induce non-trivial response at low energy. Okay. So it's at this point that I suddenly realized that the papers have been written in the past few years, like sequential circuit, and we wrote a bunch of papers with Wenjie about Michael, about the low entanglement excitations, and then these all come together to address this question of which emergent symmetry actually gives you a non-trivial response and which ones are interesting. Okay. Right, so like I said, there can be too many different emergent symmetries in a gap phase, and the question is which ones are non-trivial? And the answer is that the non-trivial ones are the ones with non-trivial defect, and now I need to define non-trivial defect. Non-trivial defect are the ones that cannot be generated using local unitary transformations. That's the way I like to define it. I'm sure other people might have other ways to say it. So for me, non-trivial defects are the ones that cannot be generated with local unitary transformations. Yes? It will be defect on the ground state, on top of the ground state. Right, so for one-form symmetry, we understand what the defect is, right? The defect is just the anyang. So we open the loop, and the anyang shows up. And this is a non-trivial defect because the anyangs cannot be created using local unitary. They can be created in pairs and then pulled away. So this is like a zero-dimensional defect, 0 plus 1D defect. Okay? And there's another very interesting defect in toric code, which is the EM duality. If we look at the Hamiltonian that I showed you a minute ago, that one is explicitly has this Z2 symmetry of EM duality because you can do a Hadamard gate and then have some translation, and then literally move the plaquette term to the vertex term, and the system remain invariant. But I mean, you can change the weight of the Hamiltonian and then lose the symmetry, right? So, so the symmetry doesn't have to be there, but in the ground state, it always reemerges. And it reemerges as an interesting kind of emergent symmetry because the defect is a non-trivial defect. And the reason we know that this defect is non-trivial defect is because there's a Marona mode at the end. If this defect is open, then there are Marona modes there. This is the non-abelian anyang kind of stuff. And because of that, if we try to generate defect line like this, it can only be generated with a so-called sequential circuit. Right? It cannot be generated as a 1D version of 1D version of local unitary, which is the one-dimensional finite depth circuit. It cannot be generated with a one-dimensional finite depth circuit. It can only be generated with a one-dimensional sequential circuit. That's what Nat and I showed in that paper. Okay. So and this all can always be done on the ground state. It doesn't matter if the Hamiltonian has the explicit symmetry or not. And this is always non-trivial on the ground state. So at low energy, I would say this EM duality always reemerges. Right. Okay, I've said that. Okay, so this is just a very quick review of what we call a sequential circuit. Because for the point-like defects, 0 plus 1D, you only need to talk about whether it's local unitary or not. But starting from one-dimensional defect or even two-dimensional defect, we need to differentiate between whether it's a finite depth circuit or something different. And this something different is what we call a sequential circuit. Okay, so one-dimensional sequential circuit looks like this, where you apply gates one by one and move from the left-hand side to the right-hand side. And it's a linear depth circuit. The depth is very high, but there are not many gates. There are only like one gate per layer. So it generates very limited amount of entanglement, but it can create some highly non-trivial entanglement limited area law states. Okay. So in one dimension, you can imagine that we go step by step from left to right. And in higher dimensions, we can go even different patterns, patch by patch, or row by row, or ring by ring. It doesn't matter. But this is how the name sequential circuit comes from. Okay, so now back to reflection. Okay, so I'm trying to claim that this reflection symmetry is something similar to, let's say, one-form symmetry or EM duality for toric code. That it is an emergent symmetry, that's okay, but I want to claim that it's a non-trivial emergent symmetry. And we already saw that because the defect gives you a non-trivial response. So we kind of know, but I want to use this circuit definition to also say that this is a non-trivial kind of defect. Okay, so this is a little bit, I need to argue a little bit harder for this case because there's physical movement of the lattice point, but let me just run my argument, and if you don't like it, we can talk more later. So let's think about this process where we start from a torus, and then we make a cut, and then do the reflection for the bottom half, and then connect it back, right? So this is the way to turn a torus into a Klein bottle. Okay, so the way I'll try to argue about it is to first say that I expect this process to be a rather trivial process if I have the trivial SPT order. but this would be a non-trivial process involving sequential circuit if this is a non-trivial Z2 SPT. Yes? The circuit, yeah. The action is only here. Oh, yeah. I'll try to argue that there's a sequential part in that. Yeah. Right. So let's think about this first for the trivial Z2 symmetric phase, where you just have, let's say in the simplest case, all plus state, right? All the spins polarizing in the x direction. Then you can put it on torus, put it on Klein bottle, and then nothing looks different. But of course, in the process, there's something tricky here because you literally need to move some lattice point from here to there, and that involves some large distance movement. So if you take count of that, that seems to already take a lot of circuit depth. But since we're trying to say that the reflection symmetry for trivial SPT order shouldn't do anything, so we should account for that as a trivial step. So we're going to say that this movement of lattice point due to the insertion of the reflection defect is a free step. Okay? We're not going to count the circuit depths involved in that. Okay? So that's the part that I need to argue harder. So for the trivial one, the reflection symmetry shouldn't have a non-trivial defect. And the defect should be introduced with finite depth circuit. So we need to assume that the moving of the degrees of freedom can be done for free. We'll not count that. And compared to that, we need to say that the same process done for the Z2 SPT needs a sequential circuit. Okay, so if we have a non-trivial SPT phase, we'll repeat the same process. We'll cut it open, and then we'll do a reflection, and then glue. But when we cut it open, there's something non-trivial happening here because we know that for the SPT order, there's something non-trivial on the boundary, right? Either you go to a gapless edge mode or there's spontaneous symmetry breaking. The gapless one is more harder, but let's say we just go into a spontaneous symmetry breaking boundary state. And then what we know is that in order to create spontaneous symmetry breaking, we need a sequential circuit. Okay? Because originally we started from something that's fully symmetric. And then we want to open up a boundary. We need to turn on symmetry breaking on one edge versus the other edge. And there's long-range correlation. The long-range correlation needs to be generated. It needs some circuit depths to be generated, and it has to be generated with a sequential circuit. So that's the part where sequential circuit comes in. And then we do this movement of the lattice side, which we assume to be done for free. And finally, we glue it back. And this gluing back is just by taking the symmetry breaking edge states and remove them. And this removal of symmetry breaking edge states also has to be done with sequential circuit. So sequential circuit comes in two places. So that's how I argue that this reflection symmetry is also a non-trivial emergent symmetry for the Z2 SPT order. Okay, any question? Oh, yeah. Well.
So your arguments are that where you argue for the sequential circuit, you don't actually use the reflection symmetry. You only seem to use the factors as SPT, right?
No, the defect I'm trying to introduce is
yeah, but
the fact that I want to cut it open and re-glue is
yes,
because,
right. But you can do that for some other symmetries as well.
Oh, you're saying I can do the process for some other SPT, yeah.
For some other whatever emergent symmetry you want to consider in the same system.
Not necessarily by cutting it open and then.
Yeah, I'm saying that in the first half of the argument, you're not using the fact that you actually need to do reflection.
Okay, right, yeah. But these spatial kind of symmetries where I need to cut open and then.
Yeah, but we can.
Usually we don't need to cut open. Yeah. Okay, so this is where we realize why we have been writing all these papers about low entanglement excitations, because these are basically the non-trivial defects The non-trivial low entanglement excitations are the ones that's generated by sequential circuit and cannot be generated by finite depth circuit, and they become the defect of non-trivial emergent symmetry. I know I'm using a lot of words that I made up, but hopefully it all makes sense. So this low entanglement excitation, we gave this term to compare to low energy excitation, which is usually what people talk about. Low energy excitations are interesting because they give you response, right? Linear response. The low entanglement excitation are not, we have in mind these, not just these point-like excitations, but also line-like and membrane-like excitations. And they're not interesting because they give rise to response because they're usually very high energy, especially when they're extended. But the reason they are interesting is because they can correspond to defect of non-trivial emergent symmetries. And so they can be point-like, they can be line-like, and they can be membrane-like. And so when we think about these defects, we think of them as ground state of some modified Hamiltonian with the modified Hamiltonian terms. So, but the system is still gapped. So these low entanglement excitations still have a entanglement area law. That's why we call them low entanglement excitation rather than low energy excitation. And the trivial ones are created with either local unitary, if it's 0D, or finite depth quantum circuit in that dimension of the defect. While the non-trivial ones are either created with sequential circuit or from a circuit of one higher dimension. Let's say the anyons are created with circuit in one higher dimension. Okay, right. And they are the defects of emergent symmetry, and whether the emergent symmetry is interesting or not depends on whether these low energy, low entanglement excitation are created with sequential circuit or finite depth circuit. Okay. Right, so let me give you one very, very simple example. Okay. Let's not even talk about SPT. Let's just talk about Z2 symmetric phase versus Z2 symmetric breaking phase. And not even SPT. Okay. So the Hamiltonian is very simple. It's transverse field with Ising coupling. And the defining symmetry, the symmetry that we want to preserve at the lattice level is this Z2 Ising symmetry, because otherwise these two there's no difference between them. Okay. And we can talk about what are the non-trivial low entanglement excitation in each phase, and then related to that, what is the emergent symmetry? What is the non-trivial emergent symmetry in each phase? And we're going to see that they're different. Okay. Right. So what are the non-trivial low entanglement excitation? For the symmetric phase, we know that everything's polarized in the x direction, and the excitation is flipping from the x direction to the negative x direction, and that gives you a symmetry charge. Right? So and if we preserve the defining symmetry, a single symmetry charge cannot be created with local unitary. We can create a pair of them with local unitary, but a single one cannot be created locally. Okay. So that's why, as long as the defining symmetry is preserved, the single symmetry charge is a non-trivial low entanglement excitation. On the other hand, if for the symmetry breaking phase, and the excitation we talk about for the symmetry breaking phase, they're the domain walls. Right? So you insert a domain wall, and here is all 0, and here is all 1, and that's the domain wall. So it's a line defect. And this line defect, very famously, if it runs in a non-trivial cycle, it cannot be generated with one-dimensional finite depth circuit, right? It has to be, you have to flip the domain on one side to generate a domain wall, right? So this is also a non-trivial low entanglement excitation. Okay, then we can say what kind of symmetry do they correspond to? If they're the defect of a symmetry, what kind of symmetry do they correspond to? So here the symmetry charge is a point, so the symmetry they correspond to is actually a one-form symmetry. Right? And it's the one-form Z2 symmetry that takes the charge and moves it around. the symmetry flux is a line defect, so it's actually associated with a zero-form symmetry, where it's the global Z2 symmetry. Okay, so it's the Z2, defining Z2 symmetry that we started from. So one take-home message here is that when a defining symmetry is spontaneously broken, according to our definition, it reemerges. Okay, for finite symmetry. Here I'm more talking about gap finite symmetries. Okay. Okay, so there's last 10 minutes, less than 10 minutes, and I'll be more speculative about why we want to talk about emergent symmetries for gap faces. They're fun, they're connected to everything I've been writing about in the past 2-3 years. But there are things that I think are too speculative to say at this point, but this is our last year, so why not? I'll just say it. And if it doesn't work, then nobody's going to come back, and, well, you guys are going to come back and find me. So, okay, but this is speculative, okay. So what I want to say eventually, hopefully, I don't know, that we think about emergent symmetries in the gap faces, and maybe that can inform us about symmetries at the critical point at the transition. Okay, so so this is actually very much inspired by the DQCP idea by all the people in the audience, and so let me just try to say why I think this is very much a DQCP idea. So DQCP is the famous idea that you start from a system with a bigger symmetry, contains two parts of the symmetry, but it gets broken on either side. So this side is G symmetry breaking, the other side is H symmetry breaking. And so this side has only symmetry H, and the other side has symmetry G. Okay. And the inspiration I take from here is not so much about the deconfined part, but rather the part where you have a larger symmetry at a critical point, where the symmetry is, again, or even bigger than that at the critical point, but the fact that there can potentially be a continuous transition is because of the mutual anomaly between the two symmetries. Okay, so if we use the emergent symmetry terminology that I just introduced, we would say that because this side is G symmetry breaking, so remember the take-home message that if some symmetry is broken, it emerges. So there's an emergent G symmetry, and on this side there's emergent H symmetry, but in the end it's the same for the critical point, because at the critical point they're put together. Okay. At the critical point they're both there. Okay. And I want to say that maybe this is something that can work more broadly, that we have gap phase 1, and we have gap phase 2, and there's emergent symmetry 1 and emergent symmetry 2, just like what we saw for the Z2 symmetric and Z2 symmetry breaking phase. And these two emergent symmetries are both there at the critical point. Okay, so nobody's throwing potatoes yet. Let's just look again at the 2 + 1D Z2 symmetry breaking transition. Yes, because I'm not looking at the audience. Yes.
Page. Yeah, you were saying at the critical point you have symmetry G and H, and then there's a tensor product. They mutually.
I'm being very. Yeah.
So the symmetry is G times H. Is it always true? I thought there's examples that in the critical point you have a large symmetry, but the large symmetry may not be.
It is even larger sometimes. It's like.
Yeah, may not be tensor of subgroups.
Yeah, there can be even bigger symmetries that encompass these two parts.
Yeah, then what's that case in your story?
Right, I don't know. Yeah, I'm not trying to. This is very speculative. This is what I feel safe to say, and whether there are bigger symmetry than just direct product of these two, or some composition of these two, Yeah, I don't know. But right, so let's come back to this Z2 example of why I think, in what way it might make sense that there's a Z2 symmetric phase on this side and Z2 symmetry breaking phase on this side, and as I was trying to argue, that there's an emergent one-form symmetry on one side and emergent zero-form symmetry on the other side, and there's emergent zero-form and one-form symmetry, both of them at the critical point. They have anomaly because the charge and the flux loop, they kind of don't commute with each other. So this is very much related to a lot of things Xiaogao, Wenjie, and their group have been talking about. And one thing I want to say is that what it concretely could mean about these two symmetries at the critical point. So there was Meng is sitting there and not throwing potatoes, but there's been a famous calculation about correlation length of domain walls at the critical point, and try to relate that to higher form symmetry breaking, if I understand correctly. And so the way we try to interpret this is maybe instead of correlation function, but rather look at the spectrum as what is done in this paper, old paper by Subir, where you put a theory on a torus and then look at the so-called Casimir energy, just lowest energy on the torus, and see what it looks like. So if you look at the energy, you will see that if you put this 2 plus 1D icing critical point on the torus and insert a Z2 defect, then there's a 1 over L energy difference. So at this point, at this critical point, it literally becomes a low energy excitation, while in the gap phase, it was just a low entanglement excitation. Okay? So at the critical point, both the charge and the domain wall become 1 over L scaling low energy excitations. So yeah, that's all I want to say. And I'm just putting myself out there, but questions welcome.